I didn't have to give a colloquium for us last spring, but now she's here as a candidate for our faculty position in astronomy. And just there's a little bit of background in terms of the last couple of weeks, but she was an undergrad at UC Santa Barbara, is that right? And then went on to Harvard to do her PhD. And while she was at Harvard, she helped found something that some of you, especially the students here, might know, which is called Astrophysics, which is a set of sort of condensed, maybe I'm hoping I'm describing it the right way, like a condensed summary of astrophysics articles for mostly for on the level for interested undergrads, and it's become really popular. And she began working a lot on dwarf stars and planets around dwarf stars. And so she's since moved on to MIT, where she's an NSF postdoctoral fellow. And we heard yesterday about some technical details at the seminar about one particular problem she's working on, but today she's going to give us sort of more of a general overview. And rather than steal her thunder, I will take it away and you tell us about it.
Sounds great. Thanks, Ryan. Let's see. So, yeah, they told me to do it. Yeah. Awesome. So it is definitely a real delight to be back here. So it hasn't actually been so true this visit, but one of my favorite things about coming to New Hampshire is getting to see stars. So I do live on the quietest possible street that I could find, but I also live in the greater Boston area. So this is my approximate view of the night sky. If I turned off my porch light, I can see about 60 stars, which I know because I counted. So I know that some of you have had the joy of going to South Africa, where I gather you can see more stars. Did any of you try to count? No? Well, your website told me that you could see probably around 4,000 stars. So somebody counted at some point. So your view there might have looked something more like this, which is why I had to turn down the lights. So now the question is, of those 4,000 stars, how many of them was an M-dwarf star? So M-dwarfs, let me tell you a bit about them, are the most common type of star in the galaxy. They make up about 3/4 of all of the stars in the Milky Way. And so how many of those 4,000 stars are an M-dwarf? So you can maybe, let's not put anyone on the spot, so just put that answer in your head. Everyone's set? Okay, great. So the answer is not one. And the reason is that these stars, in addition to being so abundant, are also the smallest and coolest and least luminous type of star. So even the closest and brightest of them is too faint to be seen without the aid of a telescope. So, this image back here, was made in planetarium software. So I just cranked up the luminosity and the red filter, and so on the nearest stars. And so you can see, if you had this view of the night sky, you'd see something very different. You'd see that these very common M-dwarf stars really dominate our view. So if, for example, you got in your spaceship and you wanted to visit each of the stars within about 30 light years, you would visit about 10 sun-like stars, and you'd have to go to 250 M-dwarfs, and you might be a little tired of it by the end. But despite all this, despite the proximity of these stars, despite their prevalence, there is a lot that we don't know about them. So for example, they have kilogauss magnetic fields. Why is that? They seem to have a lot of star spots. How many? Why do they have so many? Where are they? So there's a lot of questions about these stars, and trying to answer them is the focus of my research. So I want to know these answers in part because these are our closest stellar neighbors, and I want to know what is going on the insides of their stars. I want to know what they look like. But thinking more broadly, M-dwarfs are also really excellent laboratories for stellar astrophysics. The sun really anchors our exploration of stars and stellar physics. And these stars offer us the opportunity to conduct experiments by looking at stars that are very different from the sun. And in addition, M-dwarf stars are really excellent targets around which to find and characterize small rocky planets. So current estimates indicate that about 60% of M-dwarf stars host planetary systems of their own. And I can tell you for sure that the closest planet to us orbits an M-dwarf star. And the reason that I can say that with such certainty is that the nearest star to us is Proxima Centauri. It's an M-dwarf, and it hosts a 1.3 Earth mass planet. So the questions that really broadly define my research are, how do these stars change over time, and why do they change over time? And I have the same questions about the planets. How and why do these planets change over time? So today, I'm going to share with you the main areas of my research, what I've recently been working on, some of the things that I'm thinking about right now, and also about what thoughts I have going forward over the next years about how we can learn more about these stars and their planets. So I'm going to start by sharing my recent work on spin and magnetism in M-dwarfs and how the data that I've gathered has given us new insight into these processes. So I'll address the questions of how M-dwarfs spin down, and this is what I really focused on in my research seminar yesterday. I'll also talk about the relationship between rotation and magnetism. And in discussing my plans for the future, I'm going to address a little bit about the range of magnetic cycles that we might see on these stars. I'll then discuss how I apply different methods to characterize and better understand exoplanets. So what are the sizes of the planets around these stars, and how do young planets evolve? And in doing so, I'm going to focus specifically on one planet in particular, and I will introduce you to that planet in a little bit. So to answer these questions, we really need more data. So as we saw, M-dwarfs are not very bright, and up until now, people haven't been investing the observational resources in them that are necessary in order to answer these questions. So right now, there's a surge of interest in M-dwarfs more broadly than the community than ever before, in part because of the planets that orbit them. There, in the near future, are going to be new observational opportunities that are going to let us really make progress in this field. So this is where we're going, but in order to get there, I want to start us a little bit closer to home. And so this is the closest star to us. It's the sun. I know I actually saw it today. It was pretty exciting. So I'm also going to add some axes now. And so here we have stellar mass. The sun is at the conveniently scaled 1 solar mass. And I have drawn on here stars to the lower mass going out this way, because that is the tradition in observational astronomy. So most astronomers, to be honest, when they think of stellar physics, they're over here. They're thinking about stars that are more massive than the sun. These stars explode, and you can study them in the Large Magellanic Clouds and things like that. So M-dwarfs, on the other hand, are pretty different. So these stars are about 1,000 times less luminous than the sun. And in fact, this is just a fun historical fact. The first spectrum of an M-dwarf wasn't obtained until 1913. So the original spectral sequences that defined all of these M-type stars didn't actually include an M-dwarf. It was all the more evolved massive red giant stars. Additionally, M-dwarfs live tens of billions to trillions of years. And so any M-dwarf that was ever born in the galaxy is still around for us to observe today. Okay, and here are those stars. Here are these really awesome M-dwarf stars. So they span a really broad range in stellar mass. So going from 0.6 solar masses, which is what our early M-dwarfs are called, or these are the high mass stars, the high mass M-dwarfs, and going all the way down to the hydrogen burning limit, so the smallest of the stars, down to about 1/10 of a solar mass. So this difference in size is really important if we're thinking about exoplanets. So the two main methods that we use to find and characterize exoplanets, this is the radial velocity or Doppler wobble technique and the transit technique, the second of which I'll be talking about later. Both of these techniques rely on a relative signal. And the smaller that your planet is, the smaller its radius, the smaller its mass, the larger the signal of that planet. So smaller stars have larger signals if you're thinking about exoplanets. So another thing that changes as you go down in stellar mass is the interior structure of these stars. Stars like the sun are partially convective. So in the interior, they transport heat via radiation, and in the exterior, they transport heat via convection. And we expect a transition from stars that are partially convective to stars that are fully convective somewhere around 0.35 solar masses, so in the middle of this M-dwarf regime. So this difference in interior structure is important. And and the main reason for this for my research is that in the standard picture of the solar magnetic dynamo, the sun's magnetic field is strengthened and organized at the interface between these two regions, which is called the tachocline. So this is the interface alpha omega dynamo. So shearing due to differential rotation is also going to be key to the magnetic dynamo. And overall, there's a very strong link between the rotation of the star and its magnetic field. So stronger magnetic fields come from stars that are more rapidly rotating. The connection goes the other way as well. So as stars lose mass via the solar wind, they're losing angular momentum too. And the reason the stellar wind is effective at losing angular momentum is because those winds are magnetized. So stellar magnetism really mediates the angular momentum losses in stars like the sun. So fully convective M dwarfs should be different. In fact, partially convective M dwarfs probably should be different too, because the tachocline, that interface layer, is really deep in the stellar interior. And of course, in a fully convective star, there is no interface. The stars are fully convective throughout their entire interiors. So that means that this interface alpha omega dynamo that is often invoked for the sun's magnetic, for generating the strong magnetic field and structure, can't operate in these low mass stars. So when we think about rotation and magnetism in M dwarfs, we generally think that something should be different. There should be something different going on in these stars. So these differences between M dwarfs and solar type stars are played out in at least one area. So I'm going to show here rotation period versus age. And I've taken some rotation periods for stars at representative ages from the literature, and we're just going to look at how these stars evolve over time. So stars start out with a range of ages. Both solar type stars and M dwarf stars start out with periods between 1 and 10 days, so pretty rapidly rotating. So our sun's rotation period is about 25 days. So as stars evolve, they spin up as they're contracting towards the main sequence. M dwarfs, being a bit smaller, spin up to faster rates, and you can see that difference appearing in the data as well. So for sun-like stars, the rotational evolution, the spin-down process is well underway by about 100 million years. And by 500 million years, the stars have converged to a narrow sequence. So at a given age, a star's mass uniquely determines its rotation period. So there's this nice trend in the rotation periods. So we can go beyond 500 million years for solar-type stars, and what we see is that the stars continue to spin down. They spin down very slowly over time, still obeying this tight relationship between mass, period, and age. And over this time, as the stars spin down, their magnetic activity decays. So as they become slower rotators, they have weaker magnetic fields and have less of this thing that we call magnetic activity, which comprises all of the different tracers that we think to use as a tracer of what the underlying magnetic field strength is. So M dwarfs, on the other hand, take longer to reach their maximum spin rates. And by about 500 million years, they have just about reached their maximum spin rates, and they haven't yet begun to spin down. And so what happens beyond 500 million years? And this is something of a mystery, because the way that we have traced out this evolution for sun-like stars is primarily using clusters of stars. These clusters have known ages, and so we look at a star in that cluster, we say, oh, we know its age, we can measure its mass, this is its rotation period, and you can just put that on the plot. So this gets harder after 500 million years for M dwarfs, because none of the old clusters have M dwarfs that are accessible. So they're all too far away, and the M dwarfs are too faint. So probing what happens at these older ages has been the focus of my recent research. And we have to probe these older ages if we want to understand the spin down of M dwarfs. So specifically, I've tried to test whether M dwarfs behave in the same way as solar type stars do, when it comes to the relationship between and the evolution of rotation and magnetism. So specifically, I'm going to address the following 3 questions. So how do M dwarfs spin down? What is the relationship between rotation and magnetic activity? And what magnetic cycles are present, and what trends do they follow? In order to do this, we need new measurements. So the home base for my research has been the measurement of stellar rotation periods. So the way we measure rotation periods is from star spots on the surfaces of these stars. And we do this with by monitoring the brightness of the star. So these spots are dark, and so as they rotate in and out of view, the star becomes brighter and dimmer. So we can monitor the brightness of the star, and we can watch that brightness change. And we tend to get these very sinusoidal patterns, and this is the signature that I look for when I'm trying to measure the rotation period of a star. So this plot is the first of several that you're going to see that look like this. So it shows rotation period on the y-axis, stellar mass on the x-axis. Remember still that the low-mass stars are on this side. And rotation period and mass are both in log units for the purposes of this plot. So the points in gray here are the measurements that were available from the literature at the time when I started my work. These were graciously compiled by my collaborator, Jonathan Irwin. So my interest is in that half of the plot, where there are not many data points. So we really needed new measurements if we wanted to understand what was happening for these low-mass stars. So in the data set that I used, I was able to measure some very rapidly rotating stars, M dwarfs with periods that are measured in hours. And this is an example of one of those. So this plot shows brightness versus time, just like the PowerPoint version that I'd show you before. So this side here shows a single night's worth of data. And you can see the sinusoidal pattern being traced out just in this single night's worth of data. This particular star has a rotation period of 5 hours. On the other side here, I've taken all of the data that we have on the star and stacked it all on top of each other. So this is a phase-folded light curve, and you can see that it star traces out the same brightness pattern over the entire data set that we have. The thing that was really unique about my data set is that we were able to simultaneously probe very long rotation periods. So we measured rotation periods of around 100 days in these low-mass stars. So this is an example of what that might look like, or what that did look like for this particular star. So this is still brightness versus time, but this time the time is measured in months. And you can see that over the course of months, we're still tracing out this very nice sinusoidal pattern. So I looked at light curves like that. I looked at several thousand of them, and in the end, I identified around 350 new rotation period measurements for low-mass stars. And that's what those data look like. So you can see that with this new data set, we're really able to probe this low-mass end of the diagram. So recently, I've been working with a complementary data set in the southern hemisphere, and I'm really excited because of the very high quality high quality light curves that we've been getting with that data. And here are the rotation periods that I've measured with that data set. So this is the area that I focused on yesterday in the research seminar. So I'm going to just give you a brief overview of the results of that work. So the very first thing to notice is that there are a lot of M dwarfs with very long rotation periods of 100 days or more compared to the sun's 25-day rotation period. What this showed is that M dwarfs do definitely spin down. And this was contrary to some of the prevailing opinions in the field. So people often said that all M dwarfs were rapidly rotating and magnetically active. But we've definitively shown that, in fact, M dwarfs do spin down. And yesterday, I talked about some of the laws that might govern the spin down at late ages. I also used galactic kinematics to probe the spin down time scale. So how long does it actually take for M dwarfs to spin down to these 100-day rotation periods? And in doing so, I was able to make the very first quantitative measurements of the spin down timescale in M dwarfs. So what I found is that the rapidly rotating stars are members of the young field population of stars with ages of around 1 to 2 billion years. And at the same time, the slowly rotating population of stars are old. They're around 5 years in age. You might also notice that there's a gap between the young and the old populations. And this we've identified as a time when spin down occurs very rapidly. So stars lose angular momentum very quickly, and they evolve very rapidly across this gap. So building off of this sample of stars that I've measured rotation periods for, I've been able to gather new measurements of magnetic activity in M dwarf and probe the relationship between rotation and magnetic activity. So the tracer of magnetic activity that I've been using for up till now is the hydrogen Balmer line, H alpha. And this is the sun at H alpha. And the reason I picked this line specifically was because it's very accessible. It's very bright in M dwarfs, and M dwarfs are faint, so we need all the help we can get. So this is the sun in H alpha. This emission is created by magnetic heating of the outer layers of the star. So we use it as a tracer of what perhaps the magnetic field strength on the surface might be. So when I look at an M dwarf star, I don't resolve the disk of the star like we do here with the sun. And instead, the measurement I make is the excess amount of energy at the H alpha wavelengths, above and beyond what we would normally expect for a star's photosphere. So this is what the canonical relationship between rotation and magnetic activity looks like for solar-type stars. So the y-axis shows this relative measure of activity level, where we've normalized everything relative to the star's total luminosity. On the x-axis, we have this thing called Rossby number, which compares the rotation period of the star to the timescale for convective motions in the star's interior. So we have rapidly rotating stars over here, and these are stars for which rotation is dominating the movement of motions of in the star. And over here, we would have slow rotators. So in this canonical relationship, we have this broken power law. So stars that are more rapidly rotating than some rate have a saturated level of magnetic activity, while for slowly rotating stars, there's a decline. So stars get less active as they slow down, as they spin down. So, but research on the M dwarf rotation activity relationship has been hampered by a lack of rotation period measurements in particular. So with the measurements that I made of rotation, as well as measurements that I gathered of magnetic activity, I was able to make this diagram for M dwarfs. So here I have the relative H alpha luminosity plotted against Rossby number. I'm going to put my stars on this plot, color-coded by their stellar mass. And what we found is that, in fact, M dwarfs do display a really tight relationship between rotation and magnetic activity. So we see this saturated regime as well as this power law decay. So there are some caveats with interpreting this plot, specifically with respect to the x-axis here. And we could really use, the observers could really use some insight from theorists like Brian into a better way to parameterize this that would allow us to make more physically meaningful interpretations. But what I am confident in saying is that activity definitely decays with rotation. More slowly rotating M dwarfs are less magnetically active, just like sun-like stars. So I showed you how I used new measurements of rotation and magnetic activity to show that M dwarfs spin down with time, and as they do so, the magnetic activity diminishes. So this is very similar to what we've seen for solar-type stars. But my work raised some interesting questions as well. So I found that M dwarfs spin down, but do the spins of M dwarfs at late ages spin down, do they follow the same laws as solar-type stars? Do they spin down according to a law that tells us something about the magnetic field geometry on those stars? And what about this era of rapid angular momentum? Does this occur is this a smooth transition, or is it something that happens chaotically with one star jumping before another one does? Thinking about rotation activity, I want to know how rotation and activity relate at these older ages, at these slower rotation periods. The tracer H alpha, while really accessible and useful, is not so great at the really low activity stars. I also want to know how magnetic activity, star spots, and rotation relate to this more underlying physical parameter, the actual magnetic field strength on the star. So the data that we need to address these questions is coming soon. And I've already started gathering some data that can help us address these. So one facility that I'm really excited about is LSST, the Large Synoptic Survey Telescope. So this is the largest in terms of the size of the mirror of the telescope, and also in terms of the survey itself. So LSST is going to be conducting a 10-year survey of the southern sky with an 8.5-meter telescope. It's supposed to get first light in 2020 and start conducting its 10-year survey in 2023. And it's also going to be gathering 10 to 15 terabytes of data every night. So there is going to be a lot of data for all of us to work with. So before then, in order to get our feet wet also with the size of the data sets that we're going to be working with, we're going to be able to look at data from the Zwicky Transient Factory. ZTF's 3-year survey is going to be conducted in the northern hemisphere, which is a really nice complement to LSST. And that should have already started, and so I'm expecting the first of that data to become publicly available probably in 2019. But there's also data that we have now, where we can start looking at these questions now. And this is data from the exoplanet missions, Kepler and K2. So this data is archival and it's publicly accessible, and there's still a lot to be learned from these data sets. So these surveys are going to let us go much deeper and farther than what I've been able to do so far. So my present survey comprises a volume of going out to a radius of about 100 light years away from the Earth. With LSST, we're going to be able to measure rotation periods in M dwarfs out to several thousand light years. So this is going to open up a lot of possibilities. And the two specific questions that are related to what I've talked about today are going to be possible to answer with LSST. So in order to describe those, I want to come back to this plot of rotation versus stellar mass. So the stars on this plot are near the sun, and as such, they tend to be less than about 8 to 10 gigayears old. So furthermore, none of these stars is in a cluster. And I talked about clusters before when we were tracing out the rotational evolution of especially sun-like stars, and about how important it is to be able to pinpoint the age and stick a tack on a diagram. And none of these stars are in clusters. So the way that I've been able to assess ages so far has only been in a statistical sense. So with LSST, we're going to be able to do two things in particular. So first, we'll be able to observe stars that are significantly older than the sun. These can be field stars. But with that, we'll have the lever arm we need to understand the spin down at really late ages. So we'll be able to see if these stars do continue to spin down, and we should have the sensitivity to probe how that spin down happens. Secondly, we'll be able to look at this gap in more detail. So LSST is going to give us access to several middle-aged clusters, and we'll be able to observe M dwarf rotation periods in those clusters. Conveniently, those clusters have ages of a few gigayears, which is right where I propose this rapid angular momentum evolution is happening. So with LSST, we'll be able to see if this is happening smoothly or chaotically. At the same time, I'm excited to move forward by further studying the relationship between rotation and magnetic activity. So I'm excited about calcium H and K as an indicator of magnetic activity. It's been used before, but relatively less so for M dwarfs, because it's in the very blue wavelengths, where M dwarfs are even fainter than they are at all the other wavelengths. So this is a spectrum, two spectra that I took with the instrument Mike on Magellan. And these two particular M dwarfs, well, they have two things. First, they both host planets that were discovered by our group. And secondly, they both have very long rotation periods. But you can see those big spikes, big narrow spikes in the data, and those are the calcium H and K emission features. So despite the very long rotation periods of these stars, and the fact that they actually don't show any H alpha at all, we can still use calcium H and K as a probe for these long rotating, low activity stars. And so I also am really excited about Zeeman broadening. So Zeeman broadening lets us probe the actual magnetic field strength on the surface of the star. We can obtain a globally averaged field strength for these stars. So the data I'm showing here are two stars that are known to have very strong magnetic fields. I obtained these as part of a pilot program that I have on iShell, which is a new instrument on IRTF, which is one of the NASA instruments on Mauna Kea. So you can see by eye that these lines are split. So we can actually see the Zeeman splitting by eye, which I was actually really excited when I finally reduced this data. So the data that I have from Mike on Magellan, that survey is complete. And I have all that on, some of it's on this hard drive, but my computer's not quite big enough for that. So most of it's back at work. But what that data set really needs is someone to pay a lot of attention to it and give it some watering and fertilizer. And in terms of iShell, I'm really looking forward to proving that this method is going to work and expanding the survey with this instrument. And I've had a lot of success in the past with proposing to this particular telescope. So calcium H and K, as well as H alpha, are also accessible with SALT, as well as some of the smaller telescopes at SAAO and MDM. So this gives us a lot of opportunity to really obtain magnetic field measurements for larger samples of stars especially with MDM, and try to probe really particularly interesting stars that might be fainter, and that we might be able to do with SALT. So I'm not going to talk in any much detail about magnetic cycles and M-dwarfs, but I do want to give a brief highlight of the opportunities that will be available with LSST. So magnetic dynamos really bring together this idea of rotation and magnetic activity. So the sun's 11-year magnetic cycle is a really important part of its magnetic dynamo. And much to the surprise of the community, we actually started to detect magnetic cycles on M-dwarfs. So this is Proxima Centauri, that nearest star to us. And this plot, again, shows brightness versus time. This time here spans 15 years. The nominal LSST survey would be out to the dotted line at 10 years. And so you can see this, this overall behavior in the light curve, this very sinusoidal pattern. And this is a 7-year cycle in Proxima Centauri. And this is on top of rotation period, just like the ones that I talked about before. You can see that in the inset here. This is Proxima's 83-day rotation period. And so with LSST, we'll be able to probe this in a large sample of M-dwarfs for the very first time. So I have discussed my work on rotation and magnetic activity in M-dwarfs. And I've showed that it suggests that perhaps the differences between M-dwarf stars and sun-like stars are not as different as we thought they were. So these differences aren't as big as we thought they might be. So, and I discussed some of the ways that I want to use these upcoming surveys and telescopes and instrumentation that are already available to start probing these ideas in a new way. So I am going to switch gears a little bit for the rest of this talk because I want to share a little bit about the other area of my research, which is exoplanets. So I actually thought that if anyone had any pressing questions, that I might take those now before we get really excited about exoplanet atmospheres. Yeah?
I just have a quick question. It's intriguing that the stellar cycle of Proxima Centauri is 7 years. It's not that different from the sun. So are there other samples? Is that just random occurrence, or are they all in that kind of 10-year time scale?
There are a range. So there are probably about a dozen or less measurements of magnetic cycles in M-dwarfs, and they range from a few years to about 15. And it's related to the rotation period of the star, but the way that was described in literature isn't entirely clear. So that would be a real good starting place, is to investigate how rotation period relates to activity cycle and how that depends on mass. But there's probably not a large enough sample to say too much right now.
With the Zeeman broadening, you can get these kilogauss fields, you can measure kilogauss fields with these rapid rotators. But what is sort of the limit of the technique with sort of globally average field strength you can measure and still get detection? Yeah,
so I think it's most likely going to be down to about several tenths of a kilogauss. So the lowest detection so far is about half a kilogauss, maybe 0.3 depending on what you believe. And iShell is a better instrument for this than any of the previous ones because it's so infrared and it's fairly high resolution. But I do not yet know what the answer is going to be. Yeah?
I was curious, in using the H-alpha emission as a tracer of magnetic activity, it's interesting that it does saturate. I'm a little bit curious whether it's known what is going on with that saturation. I'm not an astronomer, I'm an atomic physicist.
Yeah.
So is it known exactly why? Is it something the magnetic transfer driving this excitation, or something in atomic physics? What's happening there?
Yeah, so it's one of two things. It's either that the magnetic field strength just doesn't get stronger at some point, like rotation only gets you so far, or it could be saturation in the heating of the outer of the chromosphere. And figuring out which of those two it is, that's still definitely an open question. Cool. And obviously, at the end, I'm still happy to answer questions about stars. I'm always happy to answer questions about stars. And so even when we start thinking about exoplanets, really what we're doing is thinking about stars that happen to have something around them. So understanding the star is really critical if we want to understand the planets that orbit them. So just as an example, stellar winds and magnetic activity could strip a planetary atmosphere. And this has been a topic coming up again and again in the literature, especially when we think about habitable planets around M-dwarf stars, which definitely are, many of them are magnetically active and rapidly rotating. So I want to discuss both how we confirm the planets around M-dwarfs, how we figure out, if there's really a planet there, what size that planet is, and I want to talk about the evolution of planetary atmospheres. And to do this, I'm going to be using one particular planet as our guide. So this planet is called K225b. It was the 25th planet discovery made with the K2 spacecraft. The little b is for the planet that orbits the star, which is called K225. So K225 is a Neptune-sized planet that is around a young star. The thing that makes there are several things that make K225b unique. One of those is that the star is a member of one of these young clusters. So we actually know how old it is. And this makes it one of only a dozen or so planets for which that's true. And of all of those planets with known ages, this one is the closest and the brightest. So the first questions that we have to address are, is this planet really a planet? And how big is it? So in order to do that, we need to take a look at the technique that was used to discover K225b. So this is a transit. It's a transit of Venus across the sun. And so you can see Venus up there. This is great. On this projector, you can also see the sunspots. So this is not what we see when we look at an exoplanet transit. The stars, in our case, are point sources out in the distance. We don't resolve this. Instead, we monitor the brightness of the star. And we look for a change in the brightness of the star as this planet marches across the surface. And that's what this looks like. So this plot shows the relative brightness of the star plotted against time. And so this dip is where the planet is crossing between the star and us. So there's two things that I want to note about this. The first is the y-axis. So the depth of this dip is 1%. That's really big. So that's big enough that my undergraduate senior thesis student last year was able to obtain a transit of this planet using the 14-inch teaching telescopes at MIT's Wallace Observatory in central Massachusetts. So she was weathered out a lot, to be fair. So I mentioned earlier that the smaller the star is, the bigger the signal of the planet. And so this planet, K225b, is a relatively small planet. It's a Neptune, but it orbits an M-dwarf star. And so that makes this a really deep, accessible transit. So the second thing to notice in this, actually you can't see it in this plot, but I'm going to tell you that each of these data points represents 30 minutes. So each of these is a 30-minute bin in time. This transit only lasts 45 minutes. And so the whole transit's actually been smeared out, giving it this V shape. So this makes it really challenging to actually confirm that this is a real planet, and also it makes it impossible to accurately pinpoint the size of the planet. So if we want to actually study K225b, the very first thing we need to do is obtain follow-up photometry. So this is something I set out to do using the 16-inch telescopes that I have access to at Marth. So meanwhile, my collaborators are also obtaining data from Spitzer, and we're both working together on different aspects of this data set. So my student, Isabel Kane, is leading our side of the analysis. So Isabel came to me as a just graduated high school senior, but she's now a freshman at Northeastern, and she has been doing a phenomenal job working on the pipeline for fitting these transits. So we spent all day on Tuesday finishing our pipeline, actually, and these are some of the fits that we got at the end of that. So both of these show brightness versus time, and the time is in hours. You can see our dip where this planet is crossing in front of the star. And the blue is the fit to the data. It's actually a Monte Carlo, or an MC simulation, so there's a lot of different lines plotted on top of each other there. So from this, we determined that the radius of K225b is 3.45 Earth radii. So Isabel is looking for signs that there's another planet in this system. So we think that there might be, because this planet is very eccentric, which is unusual for a close-in planet. And so she's going to try to measure the time of this transit extremely well, so that we can look for deviations from a perfectly circular orbit. And that would indicate that there's another planet in the system that's giving a little gravitational tug to K225b. We are also going to be investigating whether star spots on the star are affecting our measurements of the transit parameters. So this is just another plot that you've seen before, magnitude versus the phase of the rotation period. This is the rotation period of K225b that I measured from Mirth. And so we want to know whether, if a transit occurs at the peak or the trough of this, does that affect our measurement of the transit parameters? And can we use the transits of K225b to actually learn about the spots on the surface of the star? We got into this a bit yesterday, but there's a lot we don't know about spots on M dwarfs, like their temperatures and their sizes and where they are. And planets are actually a really great probe of the topography of the stellar surface. So, we need to characterize the planet. Very important. Just as important is characterizing the star. So, planet properties are measured only relative to stellar properties. So the number that Isabel pulled out of her fits is actually the relative size of the planet to the star. So this planet is 10% the size of the star. So in order to turn that into a physical size, we need to have the size of the star. In the case of this particular star, my collaborator Andrew Mann had already figured out how big the planet was, or how big the star was. But this isn't the case for a lot of M dwarfs. So figuring out ways to infer the properties of M dwarfs is something that I've thought a lot about in the past. So this plot here shows the results of one of my calibrations. So it's for the radius of an M dwarf. How big is your star? The y-axis is my best fit, and the x-axis is the known value. And the bottom panel there shows the residuals. So recently, we have applied this technique to stars with candidate planets around them. So this is a plot from work that was led by my colleague Courtney Dressing, where we applied the techniques that I developed to two stars with candidate planets that were discovered in the K2 dataset. So I've also started to work with 3 undergrads at MIT in order to analyze a treasure trove of M-dwarf spectra. Unfortunately, I was too excited at our meeting on Tuesday to take a group photo. So this is obviously not us, but could be one day. So I'm really excited. The students just got all the pipelines set up and started working with the data. So I don't have any plots to show you, but the goal of this project is to measure stellar parameters for 370 of the nearest southern M dwarfs. So these stars that our students are going to be looking at are some of the nearest and brightest M dwarfs in the south. And these are the best targets for the next generation of transit surveys to find planets around. So when we have found a planet around one of these stars, my students will have already measured the parameters of that star, and we'll already know how big the star is, so we'll know how big the planet is. So I wanted to highlight one particular example where characterizing the stellar hosts had an enormous impact on exoplanet science. So this histogram shows the distribution of planets as a function of their radii. This is a plot that B.J. Fulton made. So the x-axis here is in Earth radii. So the Earth is at 1. And we have 2 peaks in the distribution. We have one at about 2.5 Earth radii. These are the mini Neptunes. And we have one at about 1.5 Earth radii. These are the super Earths. So BJ's really big important contribution to this plot was measuring the stellar parameters. And he measured them more than a factor of 2 better than had previously been available. And without that increased precision, he wouldn't have been able to resolve so clearly this bimodal distribution. So just a short time after BJ's paper was published, Owen and Wu showed that this dip in the planet radii distribution can be explained by the evaporation of the primordial hydrogen-helium envelope of those planets. So the general model is that planets are born with this gas envelope, and then the X-ray and UV radiation from the star evaporates that away. So this atmospheric evaporation, we think, is very important for understanding the final radii distribution of small planets. If this is happening, we think that we should see it in young planets. So if this is happening, it's happening at young ages. So let's look to the planets around young stars. So this is a plot from my collaborator, Andrew Mann. It shows the size of planets plotted against stellar mass. The black points here are planets that were discovered in the Kepler dataset. these generally are going to be older stars, a gigayear, 5 gigayears, 8 gigayears. The green, brown, and red points are stars that have planets that are in young clusters. So these are the young planets. And you can see that a number of these young planets are substantially larger than we would expect these planets to be. So we're particularly excited about these two. This is K225 in green and K233b in brown. And the reason is because we want to probe the atmospheres of these planets, and we think we can do that with the Hubble Space Telescope and with the upcoming James Webb Space Telescope. So we've already been introduced to K225b. And so at its approximately 700 million-year-old age, this star is still very magnetically active. And it's going to be bombarding this planet with very high levels of X-ray and UV radiation. And so we did some basic, like back-of-the-envelope calculations, and based on those, we think this planet should be losing mass at an appreciable rate. In fact, at a detectable rate. So, let's see. So I want to try to detect this evaporating atmosphere. So this is an artist's rendition, obviously, this is actually what the data suggests the evaporating atmosphere looks like for the one planet where we have this very clear detection. It says Gliese 436b, and it has been detected to have a large neutral hydrogen envelope. It's kind of flowing out in a tail behind the planet. So I wanted to detect this for K225b. To do that, I turned to Lyman alpha. So if the planet has a neutral hydrogen envelope, maybe we can see the transit of that planet across, in the star, maybe we can see that planet suppressing the star's Lyman alpha emission as it transits the star. And this is exactly what was done for Gliese 436b. So I designed a program to use the Hubble Space Telescope to do this, and I was awarded 16 orbits to try to make this detection. So I've just about finished reducing the data, but I don't have a definitive answer yet, but I did want to share the data with you. So this is a single one of our orbits, and we've got about 300 photons, which is awesome. So the data is shown in orange, and that's the data that was included in the fit. And the fit is this blue line. So it looks funny. I know it looks funny. And the reason for that is because of the interstellar medium. So this dashed line here that you can see goes way off the plot at the top is what we think, or is what my reconstruction of the star's intrinsic Lyman alpha line looks like. So the star emitted that large Gaussian, but then that light had to pass through the interstellar medium, which has a lot of neutral hydrogen in it itself. And so that absorbed most of the flux from the star, and we're just left with these two wings. So based on this data set, what I'm looking for is a decrement in the flux of the line at these wavelengths. So whether we find one or not, it's going to be really interesting based on the fact that we know how old the star is, and we know that it has a very high level of X-ray and UV radiation. So the planet K225b is going to be a benchmark in our study of planetary evolution. And that's just because of how accessible the system is and because we know for sure its age. So myself and my collaborators are working to try to study the atmosphere of K225b, as well as the properties of the star itself, using both HST, JWST, and multiple ground-based facilities. But I want to study not just this one planet, but young planets as a population. And the way that we're going to solve that is with TESS. TESS is the Transiting Exoplanet Survey Satellite. It's being led out of MIT. There's a scale model of it in the front room of our office. So TESS is expected to launch on March 20th, which is of this year, so that's very soon. And if you're around on March 20th, I will be in Florida. I want to watch this launch. So TESS is a 2-year mission to survey the ecliptic hemispheres. So TESS takes the opposite approach of what a lot of transiting planet surveys take. So for example, Kepler had a very small field of view, and it surveyed very deeply. So Kepler and K2, its successor K2, were able to detect planets out to about 3,000 light years. TESS takes the opposite approach. So TESS has a much wider field of view, ultimately serving around 70% of the sky, but the cost is depth. So TESS only is going to find planets out to 300 light years. But that's actually great, because if we want to follow up and study planets, we need bright stars, and we need nearby stars. And TESS is going to be designed to find planets around those nearest and brightest stars. So we are expecting to find about 20 to 30 young planets like K225b. And I'm excited to work with my collaborators to follow up these planets. So in particular, I'm excited to use the 1.3 and 2.4 meter telescopes at MDM to obtain follow-up photometry to confirm the planetary nature and revise the planetary parameters. This is going to be far more important for TESS than it was for Kepler and K2, because TESS is very small, they have very small cameras, and also because the pixels are very large. So there might be there will be background stars in each of our light curves. So, and as I've learned from working with Isabel, planet transits are a really great way to start involving undergrads in research that's both exciting and important. So I also would like to use the SAO telescopes and MDM to characterize the stellar hosts in terms of both their radii and their activity levels. In addition, SALT's high-resolution spectrograph offers a really exciting opportunity to measure planetary masses via the Doppler wobble technique. So I know that efforts are underway with SALT and people working with SALT to make this happen, and I'd be really excited to be part of the effort to do that. So this is a good place to wrap things up. So it's been a real pleasure to be here over the past 2 days and to get to share my research with all of you just in the last hour. So I talked today about the changes that M-dwarfs and their planets undergo. Specifically, I showed that M-dwarfs spin down to rotation periods of around 100 days, and it takes them about 5 gigayears to get there. I also showed that M-dwarfs do indeed have a relationship between rotation and magnetic activity, and magnetic activity decays with time. I then discussed how I will use upcoming surveys, such as LSST, to investigate the late stages of spin down in M-dwarfs and to investigate this era of rapid angular momentum evolution. And I described how I'll use new and existing data sets to study rotation and the connection between rotation and magnetism and magnetic cycles in greater detail. I then turned to the planets that orbit these stars. And I showed, using this example of K225b, how important it is to characterize the stellar hosts, and about my ongoing work to constrain the properties of the planet K225b and the atmospheric evolution of young planets. And then I described how I'll use MDM and SAO to pursue these types of studies for other young planets that we'll find in the TESS data set. So M-dwarfs, these stars are our nearest stellar neighbors and our best prospects around which to find and characterize small planets. I'm really looking forward to leading a research group of graduate students, undergraduates, and postdocs in investigating some of these fundamental properties of the stars and their planets. And I'm really looking forward to sharing all of that research with both my students and my colleagues. Thank you.
Thank you very much. Do you have any more questions on this? They can ask questions about planets.
Yes, yes. You can always ask questions about stars.
Great. Do you have any questions? Yes.
Is there any chance that if you don't find the Lyman alpha?
Oh, there's definitely a chance that we don't see anything.
Would you then infer that perhaps this planet has a magnetic field that's protecting it?
Yeah, so there could be any number of things. I haven't thought about how strong the magnetic field it would need. So it could be that so the magnetic field of the planet is definitely one possibility. Another possibility is that the stellar wind is actually just blowing that evaporated atmosphere away so fast. So the pressure from the wind is
too great.
It's too great. Yeah. So those are kind of the two ideas that we have.
Do you have any other hints about how you might find magnetic fields on these planets? If you say no, I wouldn't. I
mean, there's certainly some talk of looking for radio emission from exoplanets. that's really hard, but people are definitely working on it.
Yes, decrement of lens.
Yeah.
Not a stronger question. So I was intrigued that you could use this 14-inch telescope to see these transits. Does that mean that the main barrier to people discovering these 100 years ago or something was in data processing or data acquisition or
Yeah, so we need CCDs. So you have to be able to record things pretty precisely. And
it would have been impossible like in 1918 for someone to chance on this thing and find it.
probably. It's hard to say things are impossible, but yeah. So you need you do need to do this very precisely. There's a lot of other systematics that you have to correct for before you get the nice looking light curve at the end. You have to make sure you're tracking really well. Like one of the things that makes a telescope really successful is being able to keep your star as close to one position as possible. And that's more of a modern thing.
More questions?
Why do the M dwarfs suddenly spin down rapidly?
That's a great question. So I don't know the answer, but one hypothesis is that there's a change in the magnetic field topology. So how much angular momentum stellar wind carries away is related to the magnetic field geometry. So if you were to say switch from a complex multipolar field to a dipolar field, you would all of a sudden be much more efficient at doing that. The next question would be, why do you switch magnetic field topologies? One might say a switch in the magnetic dynamo mechanism. Why do you change magnetic dynamo mechanisms? And now I'm stuck.
Okay.
I actually have one general question, which is, you mentioned that M dwarfs are 70% of the stars in the galaxy. And that's pretty easy to characterize. You didn't talk at all about the habitable zone, but the idea, right, is that it's easy to find stars that are, planets that are at the right distance, they would have liquid water.
Yeah.
Notwithstanding all the issues about magnetic activity and X-rays and other things that could affect the habitability, do we have some sense of what fraction of, quote, habitable planets would actually be found around M dwarf stars? And is that even higher potentially than the number of them?
Yes. So I think there are on average about 2 planets per M dwarf star. I can't recall exactly what fraction of those are habitable. Mm-hmm. I'm vaguely recalling some numbers, but I would be afraid of getting the wrong number out there. Sure. But yeah, there definitely are.
Like a sort of really interesting motivation from the point of view of if the stars are interesting because there are so many, but also absolutely. In terms of the planets, not only are they easy to see, but if you ask where might the civilizations live in our galaxy or some other galaxy, maybe they're actually most.
Yeah, I do think it. Well, so we haven't been able to probe the habitable zone of sun-like stars.
Right.
So it's not possible to say whether M dwarfs have more, but M dwarfs definitely do have many.
Right.
And in fact, like I showed a spectrum of I didn't show a spectrum of LHS 1140, which was a planet discovered. LHS 1140b was a planet discovered by the Mirth team, by my office mate actually, and that is a planet in the habitable zone of an M dwarf, a small planet in the habitable zone of an M dwarf. And that was one of this nearby 30 parsec sample of stars, and it was hard to find.
Cool. Any more questions?
Isn't M dwarf activity one of the greatest things? I'm sorry.
Oh.
Isn't M dwarf activity one of the greatest reasons why you would not expect to have habitable planets?
Yeah, so that's definitely a very active discussion in the field. So the activity levels are high. Especially at young ages, the X-ray and UV radiation is very high. There's actually there was an interesting idea from a colleague of mine, Sugrit Ranjan. He was looking at how much UV you need to actually start probiotic chemistry, and in that case, the activity level seemed like it actually might help. So we can be optimistic.
So you mentioned the convection difference between different sizes of the M dwarf stars and like the sun, and I was wondering if there's any observations that are associated with that kind of prediction, or if it's something that's mostly based on theoretical models or.
I believe that's mostly based on theoretical models. So there's some ways to probe stellar interiors observationally, which is namely astroseismology, but that's really only accessible in sun-like stars.
Any more questions? Right, well, we now,
Yes, we do.
having flipped the schedule, we will retire to, was there another question? Oh.
No, we need theorists.
Oh, I see. Okay.
Comment from the Phoenix.
We got it.
So we will retire for coffee in 103 right now, but before that, let's just say thank you to Elisabeth again.